Hi. Firstly, my apologies that I'm not in person today. Unfortunately, a situation arisen where I can't be here. So I thought I'd give you a short lesson on covariance and correlation coefficient. So let's go right to work. Hopefully I'll have your exams for you next week. So let's share content, screen. Okay. So we're going to talk about covariance today and correlation coefficient. So let's begin. Let's recall that we know that the variance of x plus y is equal to the variance of x plus the variance of y plus 2 times e of xy minus b of x e of y. We've already proved this a number of times. And we know if x and y are independent random variables, then this expression, e of xy minus e of x e of y is 0. Okay, which tells you then that v of x plus y is equal to v of x plus v of y in that special case. It's also possible for x and y not to be independent random variables for this to be true. I want to point that out. Okay, so this doesn't guarantee independence. Okay, now I also want to remark that if you look at e of x minus mu sub x times y minus mu sub y, we showed the last time that if you expand this, this turns out to be e of x, e of y. Oh, sorry. E of xy minus e of x, e of y. It's very easy to prove, multiply it out, and you'll see you get this. Okay, that's an interesting result all by itself. And this expression is called the covariance. Sometimes I write it as sigma sub xy. Sometimes I write it as covariance of x comma y. So what does this tell us? Well, it tells us, especially if we look at the expression in this form. It says if both x and y take values above their mean, then the covariance is positive. Or if both x and y behave the same way and take values beneath their mean, then the product will be positive also, which means the covariance is increasing. If x and y grow in different ways, if x is larger than its mean and y is smaller than its mean or the other way around, in that case, yeah, the covariance turns out to be negative. And it turns out that the covariance can actually be a number between minus infinity and infinity. So in some sense, it tells us how x and y behave together, but it's not a very effective measure because it takes such a large range. So what we'd like to do is we'd like to fine tune this a little bit, and we will very shortly, to get a better measure of a relationship between X and Y and whether or not they're literally related in some way or not. So that's what we want to consider here. Just some observations. Firstly, so we have the covariance of X and Y. Observe by symmetry. It doesn't make a difference which formula you use, it's the same. So if you replace Y with X, notice immediately it's symmetric. So the order in which you indicate the random variables doesn't matter. That should be obvious. Also notice that the covariance of, what I want to say here, of X with itself is exactly equal to E of X squared minus E of X quantity squared, which is V of X. And it satisfies some interesting properties. For example, we know the variance of AX plus B is equal to A squared V of X. It's easy to show that the covariance of, say, X plus a constant, Y plus a constant, the translation property is satisfied. It's also easy to show if we follow this, AX plus B, comma, CX plus D, suppose you want to compute this one. This would just turn out to be A, well, let's do it in steps. First it would be covariance of AX, CX, which gives me A covariance of X CY, or AC covariant of X, Y. So the properties that you expect to have follow through immediately. So we know, in fact, we already showed more generally that V of AX plus BY is equal to A squared V of X plus B squared V of Y plus 2AB times the covariance of X and Y. Now, we can do bigger and better things with these things if we wanted to. Let me just give you an illustration or two. Various properties will hold true. For example, suppose I want to compute the covariance of X plus Y comma W. That would sort of distribute out to be covariance of X comma W plus the covariance of Y comma W. And these are all very easy to prove using the properties of variance and covariance. One other remark is, suppose we generalized, okay? That is, suppose I wanted to compute something like V of X plus Y plus W. What would I do? What I would call this, say R, and then do the formula for V plus R, and then expand it again. And if I did that, this would turn out to be V of X plus V of Y, V of Y plus V of W V of X plus V of I plus V of W plus 2 times the covariance of XY plus covariance of XW plus the covariance of YW. Sort of what you would expect to happen. And of course, if they were all independent, all the covariance terms would be 0. In fact, more generally, suppose I wanted to find V of X1 plus X2 up through X sub n, right? N random variables. Well, it turns out this would just turn out to be the summation V of X sub I over all possible I values plus 2 times the summation of covariance of X sub I, X sub j, I less than j. Meaning X1, X2, if X1, X2 is there, then you don't have X2, X1. That's what this means. So let's do a silly example. And of course, if they're all independent, all the covariance terms are 0. Here's a silly example, just to illustrate how this comes about. Not that we're really interested in this reason, but we're interested in what the covariance is. It's a nice measure. Okay, so the example I'd be given in the text is the following. We have a company has a policy, realty policy. Let me read it out loud because I can't see it without my glasses. This is example number 1 from the text. The company pays monthly repair bills for plumbing and heating. And these repair bills may affect each other. So clearly they're not independent. Suppose I let X equal to the plumbing bill, the monthly plumbing bill. And I'm going to let Y be the monthly heating bill. The variance of X is $4,000. And the variance of Y is $8,000. And the variance of X plus Y is $16,000. Again, I made up these numbers. Now, they're increasing course, okay? So X is increased by a flat amount of $200 per month. And Y is increased by 15% per month. Calculate the variance of the total monthly repair bill after these charges. Okay, so you want to calculate the new variance. Okay, so what are we given? Well, we're given a lot. We know that v of x plus y well, we know all this. Let's just see what we want to find in a minute. Hold on. If we look at the given information, we're going to need to know the covariance of x and y because the new bill, the new bill would be x plus 200 plus y plus, what was it, 15% y? This is what we want to find. So this is equal to x plus y plus 1.15 y, I should say. 1.15 y plus 200. This is a constant at 200 right here, so this just becomes v of x plus 1.15 y. So this is exactly what it is that we have to compute. And now this is equal to, remember this is v of ax plus vy, this is equal to v of x plus 1.15 squared v of y plus 2 times 1 times 1.15 covariance of x and y. Okay, now we know v of x. V of x is equal to, where's v of x? V of x is equal to 4,000 plus 1.15 squared. V of y we know. V of y, where's v of y? V of y is 8,000. But what we don't know we have to find covariance of x, y, but we could do that. How? Yes, we know that v of x plus y is equal to v of x plus v of y plus 2 times the covariance of x and y. Well, v of x plus y we were given somewhere or other as 16,000. V of x was 4,000. V of y was 8,000 plus 2 times the covariance of x and y. So what is that? 8 and 4 is 12, 12, 4, 2, is that 2,000? So we have we can now plug in. So this turns out to be covariance of xy. What did I just say? It's 2,000. Substituting in here, we get our result, which is $19,180. Now, this is really a contrived problem, but it's just to show you that one can figure these things out if one needed to. And I actually got this problem off an old actuarial exam some years ago. So I wanted you to see that. Okay, now, I mentioned a little while ago that the covariance in a way measures dependency or linearity or relationship between the random variables x and y. But the problem with that is it could take a large range of numbers. It's not well behaved, so it doesn't give us a lot of useful information. A minor change in variables can give us a much greater change in this number. We'd like a number that's much better behaved. So to that end, we define a new concept called the correlation coefficient. It tells us how x and y are going to be related in a nicer way. Correlation coefficient. And these are important ideas in basic statistics. So we're going to define it in an unusual way, and we'll get the equivalent. So let's suppose, so given the random variables x and y with mu sub x, sigma sub x, mu sub y, sigma sub y. So I'm giving you random variables x and y. I'm giving you their mean, and I'm giving you their standard deviation. And let's define, let x star be a standardized version of x. And y star will be the standardization of mu sub y. Okay, and we define the correlation coefficient and the symbol for that will be rho of x and y to be the covariance of x star with y star. I'm assuming, of course, by the way, that sigma sub x and sigma sub y are unequal to 0. Okay. Because if sigma sub x and sigma sub y were, that's a special case, and we'll call that, then we'll say the correlation coefficient is 0. So I've defined this correlation coefficient. And by the way, when these are not related, when rho is equal to 0, when rho is equal to 0, we say they're not correlated. So this is not the usual definition that one sees for the correlation coefficient. So let's get the one. So let's get the definition. So this is our definition. So now let's observe that, in fact, covariance of x star y star, I'm going to now use the properties, is equal to covariance of x minus mu sub x over sigma sub x, y minus mu sub y over sigma sub y. Now, if I use the properties of covariance, which are very similar to the properties of variance and expectation, I can pull out the sigma sub x and the sigma sub y. And then the translation properties come into play. So this becomes 1 over sigma sub x, sigma sub y, times the covariance of x comma y. And lo and behold, we end up with rho of xy is equal to the covariance of xy over sigma sub x, sigma sub y. So this is written a number of different ways, as I've just written it, or if you want, I can write it as sigma sub xy over sigma sub x, sigma sub y. Or if you like, covariance of xy divided by the square root of the variance of x times the variance of y. They're all the same. So we have this really nice result for this correlation coefficient. And then we'll look at some of the properties. So we've just shown that rho of xy essentially is nothing more than the covariance of x and y divided by sigma sub x, sigma sub y. Now, why is this nice? Suppose we have two random variables, x and y, and we make a linear change of variables. That is, the new variable u is equal to, say, ax plus by, and maybe v, this new random variable, is equal to, I'm sorry, not ax plus by, ax plus b1, a linear change. Ax plus b and cx plus d. So the question is, how is rho of uv related to rho of xy? So let's compute it. Rho, the correlation between u and v, is covariance of u and v divided by the variance of u times the variance of v. I'm using two different v's. Let me squiggle one v, okay? Okay, so u is equal to ax plus b, cx I'm sorry, cy plus d. This is cy. cy plus d over v of ax plus b times the square root of the limit, right? V of cy plus b. Okay. Now I'm going to use the property of covariance and variance. So this becomes covariance of ax comma cy over, remember the linear terms disappear, the square root of a squared v of x c squared v of y. This gives me AC covariance of xy over absolute value of AC sigma sub x sigma sub y. Notice this is just, this term right here is the original rho of xy. So rho of uv is equal to AC divided by the absolute value of AC, here the plus or minus 1, times the covariance, the original covariance. So what does this show? This shows that a linear change in random variables, at worst, it'll change just the sign of the correlation coefficient. Now we say if the correlation coefficient is close to 1, by the way, this is typically what we do in statistics. If the correlation coefficient is close to 1, then we say they're linearly related. There's a strong linear relationship. If it's near 0, it's not at all linearly related. Well, that's a pretty interesting observation. Here's an example from the text. That is, so now, let me illustrate. So how do we actually find rho of xy? Well, remember what rho of xy is. Rho of xy is the covariance of x and y over sigma sub x, sigma sub y. So these are come from the variances. And now to find this term, this is just e of x y minus e of x e of y. So you go back to one of these tables, you work it right off the table, you can find rho of xy, as you'll see in a couple of examples from the text. Maybe I'll do one in a couple of moments, but I just want to illustrate some other results. Now, I want to talk about this number rho, and I'm talking about it because when you take statistics, it's an important idea there, so I want to make sure you understand it. So rho of xy, the correlation coefficient, gives you a relationship between linearity, basically. We're going to see if it's close to 1, things are linear. If it's away from 1, in fact, I'm going to prove in a moment, it's always between -1 and 1. So maybe I ought to do that first. Theorem. Okay, theorem. Rho of xy is a well-behaved number. It's always between 1 and -1. Well, how do you go about proving that? Well, if you remember the definition we took for rho of xy, rho of xy well, before I do that, let me consider the following. Consider v of x star plus y star. Where x star and y star were defined to be the standardized ones, as we did a minute ago. We know this is equal to v of x star plus v of y star plus 2 times the covariance of X star and Y star. Okay, so just a simple whatever. Now, these are standardized random variables. So V of X star is 1. V of Y star is 1. And this is just plus 2 times rho of XY. And we know the variance is always positive. So this has to be a positive number. So this tells us immediately that rho of XY is always greater or equal to -1. Now I can do the exact same thing again and look at V of X star minus Y star, which is also going to be greater or equal to 0, by the way, because it's a variance and the variance is always positive. This is equal to V of X star plus a V of Y star plus 2 times 1 times -1 rho of X, Y. Same reasons before. So this gives me 1 plus 1 minus 2 rho. And I know this is greater than or equal to 0. And this tells me rho is less than or equal to 1. Putting this together, we see that the correlation coefficient will always be a number between -1 and 1. That's a nice result. And that's why it's so beautiful. That's why we now have a measure. Instead of using sigma of xy, we replace it by rho of xy, because sigma is not well behaved. You can take on any value between -infinity and infinity, whereas rho of xy, which conveys the information you want about independence, about correlation, about linearly related, is always a number between -1 and 1. And the converse is also true. And the converse says the following. It says, suppose rho of xy is plus or minus 1. Then, with probability 1, the relation between y and x is linear. For some m and b. So this says, if in fact the correlation coefficient is plus or minus 1, then the relation between m and b is almost linear. And we can show this pretty easily. We already showed that when rho is equal to 1, we just did this a moment ago, we showed that, what did we show? We showed that V of X star minus Y star. What did we show before? Turned out to be 2 times 1 minus rho. And we showed if rho is 1, this is equal to 0. And we already proved using Chebyshev's inequality that if the variance is equal to 0, the variance of some random variable, of any random variable, let me just say it this way then. So by Chebyshev, that means all the information is concentrated at the mean, right? If the variance is 0. So that means X star minus Y star is a constant, right? By Chebyshev, the variance is 0. The only way the variance can be 0 is everything concentrated at the mean, okay? And now if we solve for, remember what X star was. X was X minus mu sub X over sigma sub X minus Y minus mu sub Y over sigma sub Y, all this equals C. This enables us to solve for Y as some function of X, whatever m turns out to be, plus some number B. Now that's pretty cool. This last sphere on my earth here. Similarly, if X and Y are linearly related, we can then also show very easily the same way that the relationship between them is the correlation coefficient is either 1 or -1. So let me sort of survey. Okay, so we define the covariance of X and Y. There's two definitions. Equivalent definitions. There's nothing to do with this. We know if X and Y are independent, covariance is 0. Converse not true. Meaning non-independent random variables can have a covariance equal to 0. The properties of covariance are very similar to the properties of variance. Namely, this would just turn out to be AC covariance of XY. There are a whole bunch of these that I give you in the text. We define the correlation coefficient. Well, we prove that the correlation coefficient, which is as a convenient formulation. Or if you like to write it this way, over the square root of the variance of x, variance of y. We know the correlation coefficient is always a number between -1 and 1. When an absolute value, when the correlation coefficient is close to 1, x and y are linearly related. Okay, now, how important is correlation coefficient for us, really? It's a nice tool, something to know about. It's more important for statisticians, I think, than for mathematicians. And we shall pick up on that very, very shortly. Okay, so please make sure you do the homework exercises in section 2.10. In section 2.10. Now, I just want to sort of move ahead a little bit and just tell you what's happening next. We're almost ready to hit the big time, basically. That is where what comes next is we really want to examine some really important probability distributions. We want to get back to probability, not statistics. This is really a course in probability. This was just a little outing in statistics, which is important for some of your other courses, especially in Zicklin. Okay, now, in order to minimize the amount of work we have to do, we introduce a new idea called the moment generating function, which I'll just talk about in a moment. So let me just talk about a moment. We've already talked about moments. The mean, so given the random variable x, its mean is often called the first moment. So we can talk about higher moments as well. So, for example, e of x squared is used when we want to compute the variance. Sometimes we'll call this the second moment. So I might call the mean sometimes the first moment. E of x squared I might call the second moment. And I could generalize this idea and I can call e of x to the k, from the use of k, the kth moment. Now, I want to remind you from calculus about the number e, which was about 2.71828. Then it does a whole bunch of weird things, whatever. About 2.7. Its formal definition, remember from calculus, is the limit how do we do it again? This was the definition of the number e, or one definition of e. How did this come about? This came about through calculus. We were looking to find derivatives of the exponential function. Of course, if you try to evaluate this, you get 1 to the infinity. Now, another definition, another use of property for E. We're gonna talk about expressions, exponentials. So let me remind you or tell you the following fact. E to the x can be written as, one can prove in calculus that this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on and so on forever. And this converges for all values of x. Sometimes we write this more succinctly as and this is an important number. We've seen it in calculus a lot. It's the base of the natural logarithms. And it turns out it's going to be very, very useful for us, because it turns out that we could talk about a random variable, E raised to the random variable power. Now, why is this useful? Because you're going to see that this will generate all the higher moments. So this would just equal to the summation. Actually, what we're really going to be most interested in is not so much of e to the x, but the expected value of e to, say, t to the x, where x is a random variable. Now you might say, wow, what is this about? Well, it turns out that using this, we get, this is called a moment generating function. This will generate all the moments, and you'll see the importance of that. Now, this is an appropriate place for me to stop, but I just want you to remember that we're going to start looking at calculus very shortly. And this will be a useful trick in helping us study some interesting probability distributions. Okay, hope to see you guys on Monday. Let me stop this recording now. Here we go to Zoom. Okay, here's back control. Any questions, just send me an email. I'll try to answer them. And I hope to have your papers for you on Monday.